All right, so again, this is for worksheet 13.3. Now, this is part 2. This is just giving you some more examples. I'm going to do 2 more for you, and I think I'll post like 4 examples of my notes so you can take a look at a couple more of these. So, again, what we're doing here is find the arc length parametrization. Okay, so basically take an equation, RT, t squared, 5 and 1, okay, and we'll say the time is greater than or equal to 0, and basically converting this into, in terms of where you are the time, but convert it into a distance, and where would you be? All right, so let's look at, like for example, when, let's say t is 2, in terms of your location. So that would mean then R2, you would be at 4, 5, 1 would be your location here. Okay, now to find the distance that you have traveled during that time. So remember, you have to use the Pythagorean theorem. So you got to do the derivative squared. So r prime of t. So you have 2t 0, 0. And therefore the length, the distance you traveled there, has to be integral of 0 to 2. And that would be 4t squared plus 0 dt. Or clean this up. This would be integral of 0 to 2, 2t dt. Okay, that's right. Yep. So therefore, it would be t squared from 0 to 2, which would be 4. Okay. All right. So there's your distance. Now, so let's take a general thing here. So from this piece here and this, let's say this is S equals, actually let's just do this piece here since we already did it. But changing this, so we have t squared from 0 to t. So basically we would have t squared, and therefore t would be the square root of s. Okay, so if we plug it back into our equation here, and then we can rewrite this again so we can see it. So RT was t squared 5 and 1. So now replace this for the other t, so you have now r of s. That would give us s, 5, 1. Okay, and sometimes, like I said, you'll see this written like a function composition where you have rg of s, of s, 5, and 1. Okay, so if we look at, let's say, we know our distance we found up here earlier, in red here, we found a distance of 4. So if we plug in, say, rg of 4, then we have a location of 4, 5, 1, which we have from up here. Where was it? 4, 5, 1. Okay. All right. Anyway, so now you have an equation representing, if you have a certain distance. So let's say my distance is now, like say 10. Where would it be with a distance of 10 units? What's my location? So I'm not using time anymore. I'm using this. Okay. All right, let me go through one more example. Okay, so let's use r of t squared, and 4. Again, we'll do t greater than or equal to 0. All right, so let me see here. Let's find the distance of when t is 4. So that's what we'll compare by. So when t is 4, where would it be? So r of 4, my location would be 16, 16, and 4. So this is where we will check our answer later on. Okay? All right, so let's go ahead and find how far that is between 0 and 4. So use the Pythagorean theorem, r prime of t, 2t, 0. Okay, so s be the integral from 0 to 4. Square root of 4t squared plus 4t squared plus 0 dt. What were they here? That'd be the square root of 8t squared dt. My values would be square root of 8, 0 to 4t dt. And square root of 8, so you have t squared divided by 2 from 0 to 4. And what we got here? Looks like square root of 8 over 2 and 16. I go this way here. So we have 8 root 8, or what's that? 8 times 2 root 2, 16 root 2. Okay. All right, so that's our distance. So we're going to use this to plug it in and see if we get the same values. So when we plug in, we should get, was it 16, 16, 16, and what was it, 4. Okay. All right, so let's come up with a general scenario. And the best way to look at it would be right here at S. Okay, so we're going to go S equals, and let's clean this up a little bit here, make life easy. That'd be 2 root 2 over 2 t squared and 0 to t. Okay, so that would be root 2, and that would be t squared. So it would be s over root t equals t squared. And now take the square root of both sides. Okay, I would have t equals the square root of s over t to the 1/4 power. Square root is 2 to the 1/4. All right, so now we're ready to substitute in. So let me come back and rewrite our equation here. We had RT of 2t, oops, wrong one there, t squared, and 4. Okay, so what we want to do here is take this and replace each one of those. So if you square each one of these, so t squared, basically come back here, so t squared is s over root 2. And this would be r of s now. So I'd have s over root 2, s over root 2, and 4. Okay, so now, and again, this might be written as r of g as s. This. Okay, so let's check to see if it will work. Now, we said our distance was 16 root 2, and with that we should get 16, 16, and 4. Okay, so let's plug this in here. So r of 16 root 2. So I would have 16 root 2 over root 2, 16 root 2 over root 2, 4. So I am located at 16, 16, and 4, which came out. But like I said, now I have an equation to deal with other things for distances. So if I want to say, okay, where would I be if I traveled a distance of, let's say, 32, okay? Or let's say a distance of 60, okay? So I have an equation to use it for other measurements other than just time. So anyway, I will post 2 more examples on my notes so you can kind of take a look at those two. One of them is the helix graph, dealing with your DNA. You know, instead of time that you travel on your DNA, which doesn't really make sense. You know, your DNA actually is a distance. So you want to deal with, you know, how long, where would you be with the length of your DNA? So that would be one of my examples that I'll have posted online. And this is just a single helix, not a double. Or your DNA is a double helix. So anyway, take a look at that one too, in terms of how your DNA would be represented by, not by time, but by a distance. So hopefully you can kind of wrap your head around that, especially for those who are thinking about going into something of science, of how things might be represented by length, not by a time. All right.